So more important to be corrected fast. If performance is a requirement for your application, then you need to make it a requirement. It needs to be written down, and you need to have, reasons why this number is needed.
Dennis, it's great to talk to you about HPC today. Now, a lot of people are not really going to know what HPC is, and I'm not really an expert either. I've kind of skirted around the edge of it a couple of times in my career and built one HPC system, but debatable how you'd consider that HPC or not. So for those that don't know, what is HPC?
Yeah, no, that's a good question, John. I'll caveat with our little pre-discussion here. When I first joined software development, I thought everybody knew what HPC was, and I didn't realize it was a niche little area in the corner of programming. And I joined a local development community and told the people I worked in HPC, and I had somebody type in little Slack chat, what is HPC? So that's a good starting point. So HPC stands for high performance computing. And say, like, traditionally HPC, you can think of like a data center with a lot of computers just networked together by a very fast network and very fast storage, or place where you put your data. And in that setup, your application might use, some of the cores in the big data center, or like in these larger scientific computing or machine learning applications, they might use all the cores. So you could have a, 15, your computer has some, maybe modern computers have, my laptop has 16 cores in it, 16 processors. So you might use all 16 or just a couple, speed up your application to parallelize things. And then they've made nice software and even hardware optimizations and stuff to maybe take one of my laptops and then stick another one beside it and use all the cores in both laptops. And they have scaled that out with much larger computers. And it's really common in scientific computing, where you might be doing physics simulations on particles, or computational biology, genomics, and these large language models, all that stuff just blows up and likes to use a lot of compute.
Yeah, so that's kind of different to the impression that I always had before I got any experience of it. I always imagined that HPC was this grey computer that I'd seen in a textbook as a kid, which was this room full of computer, the stereotypical Cray that had that bench kind of goes down the middle. Looks like something out of a sci-fi film. But my first exposure to HPC was, like you say, it was, there's 400 machines in a data center somewhere. They're all connected up with some high-speed network. You're going to build your software and deploy it on there, John. And that was quite a different perspective to me. Yeah. So how have you found that HPC differs from traditional development? What's a different experience that you have?
Yeah. I think one of the kind of the main, I'd say, flow differences from a day-to-day perspective is that I am generally always like remote logging into some terminal that exists somewhere else. And now they have, IDEs, VS Code has SSH connections, and whatever your favorite flavor is, they can do it pretty well. But you log in, and then this very common tool in HPC is this batch scheduler. So some common ones are called Slurm or LSF. I think those are, Grid Engine was one, and there are many. There have come and gone many. Grid, Sun Microsystems, but this batch scheduler is a way to allow users to share all the cores in this data center without stepping on each other. So because all this this development is going and launching off to remote computers, the scheduler, let's use Slurm as an example, does a good job. So I write my little Python application, and let's say my application just uses one core. It's just a simple serial application that reads some data and processes it and spits out a result. This scheduler would allow me to work on this data center, let's say with 1,500 other developers or users, where I can launch my computer. The scheduler is going to handle which core of these 400 computers that it goes to, how much memory it's going to use. So let's say I'm going to use 10 gigabytes of RAM, and it's going to take that slice out of the whole pie, right? It's going to block that from other people. And kind of this submitting to batch schedulers is a very common pattern in HPC development when I'm doing like application testing and development. And if you scale that out to, I also realize that then maybe I want my application to use 2 cores or 10 or one whole machine. I think not a ton of developers are super exposed to parallel computing, like early on especially, and whether you're doing, and then you can get into all that, but whether you're doing parallel computing like within a single application, or you're using your application to only process like a little chunk of data, and then you're launching it again with this next chunk of data. There are a lot of different ways you can do it, but that's another kind of mental model shift, is you sort of try to think about things and how you can chunk up data to process it using all the cores at your disposal. And so those are probably 2 main, like a difference in flow and then a difference in thought about approaching development.
So just on those batch schedulers, I mean, my solo experience was using LSF, and we didn't really use much of the power of it, but I still found it amazing, having come from working on some desktop applications and some web applications, to then go back to this command prompt. And I'm almost writing what feels like a bit like a bash script to access the most powerful computer I've ever worked on.
Yeah.
It felt very strange in that environment. But it was also awesome that in a couple of lines of command line code, I could take what was a Python program then, a primarily Python program, written using Dask and Dask distributor, and say, I want to run this on one node with 20 cores on that node, or I want to run it on 200 nodes and use like thousands of cores. That power and that ability to distribute that work felt quite amazing.
Yeah. It's pretty fascinating too, like how well these modern programming languages and frameworks even have abstracted away the need for us to like go in and tell our program, use like this block of memory and like give a pointer to it and then pass that pointer to a remote machine, because there's all that too is stuff that people used to have to deal with. And they've done an amazing job like cutting a lot of this out, so we don't deal with that complexity anymore too.
Yeah, I was hugely impressed with Dask and Dask distributed, because it's framework built in Python, and for a few decorators in Python you can kind of specify this computational graph. And it will even draw you the graph showing you the computation flow. So then you say, right, you've got the graph of all this computation we've done, go and distribute it across these different nodes.
Yeah,
it's amazing and powerful. I think that's a bit different. You've done a lot of CUDA from what I've seen. So first off, for people, what is CUDA, and how does that differ in how you're using it?
Yeah. CUDA is NVIDIA's programming model or programming language, and it is for GPU development. So, it initially came from, like in 2004. this guy, Ian Buck. He was a PhD student, and he spent his PhD kind of thesis playing video games with his friends, or doing a lot of Quake back in those days. Yeah,
I was
and
struggling not to interrupt there, Dennis, because I was thinking I know CUDA from Quake, and me and all my friends recently graduated from uni with our NVIDIA cards. Like, yes, Quake will run faster.
yeah, and he and his buddies would like hack together Quake servers, and he would need to program the graphics cards to do that. And I actually saw him give a talk, and like one of the programs that he had to write to just do something very simple in Quake was this, let's just say 1,000 lines of code just to jump into that graphics card and tell which part of his application where it needed to run on the graphics card. So he set out to essentially make graphics programming easier, and he had a paper called Brook, and I think that was his thesis. And Brook was the first kind of intro to CUDA. And while he was doing that, he got to internship at NVIDIA, and eventually they took him on after. And many people don't know this, but it was like over a decade really before CUDA had real utility anywhere besides development in NVIDIA. It was a long road leading up to it, and I think they spent a lot of time figuring out who their use case would be, but they knew they had something there, in that like he had shown that for scientific computing, using GPUs or using graphics processors, right, he could cut down scientific computing from some big workflow from, like, I don't know, 6 months running on one of these data centers to 1 month, which is pretty significant, right? It's a huge boost in the amount of research you can do, and the turnaround time before you get your results and all that.
So, Dennis, why is that? A lot of people won't know. How do we get from GPUs, graphic processing units, that let us play Quake faster, which was awesome,
Yeah,
and the predominant programming model on that was like Direct3D or OpenGL.
right.
And CUDA came along, but how did GPUs lead to actually being useful for HPC? Because a lot of people won't know this.
That's a great
And again,
question. Yeah,
I've got a vague idea, but I'm not sure.
yeah, that's a great question. So, couple different paradigms there. So, like I brought up my laptop earlier. It's got 16, we'll say, cores for running all of the applications. So we have a core running this browser, and maybe a couple, probably a few, working together to get this going. So CPU has a few cores, and they're very good at generalized tasks. So even at the hardware level, they're kind of designed to do some pretty complex branch predictions and figure out just efficient ways to switch between threads. So I can be on this browser, and then I can click over to a Microsoft document to type things, and come back and check out my email, and it can context switch very well. And like a graphics processor blows that number of cores way up. So let's go from 16 to 1600, right? And has a ton of these cores, but they're not very good at general computing. They do specialized tasks very well, and that may be like image rendering back in the day. And now they have a lot of ALUs, arithmetic logic units, and they're very good at, let's say, a smaller number of instructions. And if you go outside of those, smaller number of instructions, they're not going to do what you need them to do. So CPUs are designed to diminish latency. So when I jump from recording to email, there's not like, a 2-second lag time before I can use my email. It happens instantly. I can jump in pretty much and start doing that. But they're not great at throughput. So if I, sent a million, or let's say a billion instructions at my computer at the same time to a single core, it would have to, churn through these and figure out what it needs to do. And it's not going to do a great job getting through all 1 billion of those instructions very quickly. GPUs are kind of paradigm flip there. They're not great at latency. So my first answer isn't going to be super fast. So in my email scenario, let's say it could do all that. That response might take 2 seconds or less. They're fast, but it's going to process through those 1 billion instructions, especially for special applications, much more quickly than a CPU will. So I like to think about it as a wave, right? It's like this, people can't see my hands if they're just listening, but like the wave moves forward slowly, but it covers a broad swath of things, whereas the CPU maybe is more of a point and it just bounces back and forth really quickly.
So, Dennis, I kind of think of that as the CPU is going to process like one calculation that we're doing, one calculation and one bit of data very, very fast. So, if we want to, say, calculate a Mandelbrot set, we can plot one point really quickly. Whereas the GPUs, I think, if I understand this right, they're very, very good at working on vectors or very, very good at working on matrices.
Yes.
Which, of course, perfectly fits, rendering Quake and doing 3D graphics.
Right.
And also perfectly fits so much of machine learning and modern AI. Or neural networks, quite often we calculate with matrices, don't we? And a lot of other areas of machine learning, it's all matrix multiplications. And as you say, once you've got a matrix and you've got 1,600 cores, for example, or 16,000, sorry, I can't remember which it was, but you can get a pretty good matrix very, very quickly when you're doing that all in parallel, can't you? Versus a single CPU is going to have to do every single cell of that individually.
No, that's exactly right. Yeah, if we think about that from the perspective of where they're used, like math, basically, or small math operations, matrix operations are highly parallelizable, in that, like, you can essentially, let's say you have a big matrix with a lot of rows, you can essentially do an operation or a calculation on each row individually, right? There's no relationship between row 1 and row 2 for, like, let's say a multiplication. And so for applications or operations that don't have a lot of data dependence, where one data point is async or disjunct from another data point, that's like the absolute best use case for a GPU. You can just throw all that work there and let it churn. Yeah.
So, as you say that, I'm starting to think, I can imagine another bottleneck now happening if you're dealing with a big set data center full of GPUs. You can do, as you say, amazing throughput with all these matrices. I'm starting to imagine that you could have a real problem feeding enough data into this.
Yes.
Shuttling data across the network into memory, distributing it. How do you manage all that data? Actually getting, how big are these LLMs in the training data? There must be terabytes of data.
Yeah, absolutely. It's interesting. This is probably one of the more studied areas right now, and one of the areas that's also driving a lot of development. So data movement, which is what you're describing, is the real bottleneck nowadays in HPC, in that, because data has gotten so large and you're operating on all of it at the same time, you are sending it to many different GPUs, let's say. And let's say I have 1,000 GPUs with a couple thousand cores each. They're all doing their own operation. And the way these models work is or programming models, let's say for machine learning, tends to be like a fan out and a fan in back, approach, in that like we'll send out a lot of parallel operations, but eventually we do need to converge on an answer. So like your LLM or your inference, your chat GPT will respond back to you with, you ask it a question, give it a prompt, it'll write you back a message, right? That message is really a lot of stuff going out and doing parallel work and then coming back together. And so the GPUs, they need to communicate. They need to be able to talk to each other to kind of converge that result. And there are a lot of techniques. So one is RDMA. That's a thing people aren't maybe super familiar with, and that's remote direct memory access. And that means computer one over here can see memory spaces in computer two, and they're connected by a network, and a very fast network. So let's say like 400 gigabit per second or gigabyte per second network speed. They can communicate memory back and forth. So that's sort of one way that this is, let's say, accelerated.
So just quickly jump in, Dennis, because I'm curious there. Presumably, when you're talking about that, that's an incredibly high-speed network. Presumably, that's a very, very short network.
It is.
And you're avoiding any switching, you're avoiding any routing there, and literally two machines next to each other, direct cable connection, presumably.
Yeah, that's where kind of I'd say this specific area is a main difference between high performance computing and something that more people are familiar with, which is like distributed computing. Because you can do this you can do HPC on CPUs also, and it leverages RDMA. And so that is the construct of a data center. Like in a cloud application, I could maybe run part of it here. You abstract it away and throw some compute here, and then you might even do some compute in another data center that is some remote land, and to you it doesn't matter. It's all fast enough. But in these applications, the concept of the data center and even the networking within the data center, how the different computers are arranged at the network fabric layer and how they're plugged together literally can reduce the latency of communication between machine one and machine two, going over this super fast network.
So presumably then you're at the level of building your own top of rack switches, minimizing the routing, making it
huge
direct as possible.
Switches. The new release from NVIDIA this year was the GB200, and they are basically putting the switch and all the GPUs in the same box so that it's all just happening very, very close together. Like physics is a real bottleneck here. And so we can't extend that like RDMA cable, let's say, over miles, because you get photon or electron dispersion, right? We start to have our connection, our signal just disperse.
You're going to get latency just from the distance, aren't you? Even with speed of light, you add a couple of 100 kilometers and you're going to add some noticeable latency.
That's right. Yeah.
Cool. That's interesting stuff. I kind of miss playing with networks and data centers now.
Yeah. It's really fascinating when you're, and like I said, even so, CUDA, nowadays people would consider CUDA to be low level and maybe challenging to work with. CUDA was actually designed to simplify graphics, right? And it's fun to jump into CUDA and use these abstractions that they've made to, have calculations run on multiple GPUs and see a virtually linear speed up, right? I'm going to give you a whole nother GPU to work with for my matrix multiplication, and I'll pretty much see that specific calculation just speed up linearly with the number of GPUs I've given it. Yeah, which is cool.
So if CUDA's becoming quite low level, what's kind of abstraction people are using on top of it?
Yeah, so nowadays it's really Python. All of this programming. So CUDA team.
Sorry, Dennis, but Python's slow. You can't use that for high performance compute.
Yeah. No, that's the conception, and maybe I won't really call it a misconception. So that's true. But they're writing these amazing kind of bindings. So we're really using CUDA. Somebody is writing this code in a lower level language. They're doing it, for other stuff like CPU data processing in Rust, or C++ for like NumPy, numerical Python. They're writing these in a very optimized portion of lower level language, binding that back to a Python function. And when you're calling that specific Python function, it's running, let's say, much more quickly using that lower level language. Yeah.
See, now there's the irony of my HPC experience. We built everything in Python using Dask and Dask distribute, as I mentioned, but actually the components we were testing and putting together, we were testing the validity of machine learning algorithms. We were actually comparing algorithms, some in C, not for performance, but because we were verifying the code that was going to run on an embedded device perform correctly, and some in MATLAB. So we were pulling components in MATLAB and creating a Python wrapper then, so we could test experiments of what the researchers were doing. But I was still amazed, actually, at the sheer throughput, because the original system that was built for this took a week to learn.
Yeah.
We reloaded it in Python, put it into this HPC cluster we built, and typical experiment could have been done in a few minutes then. It was amazing speed up, even with the bits in MATLAB and so on.
Yeah.
But yeah, it's interesting to see that Python is being used, and you say it's more of a glue, isn't it? We're using its power and leveraging things like PyTorch and other frameworks there that are all built on top of CUDA and extracting that.
Yeah. It's I call it an API layer. It's like just this nice plug that connects our a simple programming language into maybe something that is more complex. It really is. It's amazing. So like when I was at my old job, we would kind of prototype things in Python, and just make sure that we got, let's say, correct behavior, correct calculations, and something that took like 2 lines of Python. So CUDA has this library called CuPy numeric, right? And it's essentially a drop-in replacement for NumPy. So anywhere you could use NumPy, you can use CuPy. It was like 2 lines of Python code was like 250 lines of C++ code when I wrote it from scratch. And it was for like a fast Fourier transform. It was amazing. And that's super nice. I would rather use that 2 lines and it runs just as fast. It's the same. It's running the same.
You've perfectly described why I moved from C++ to Python.
Yeah.
Because I started my career doing a lot of C++, love C++, but it got to a point, it's like, why am I writing a makefile? Why am I doing all this work?
Yeah.
In Python, that would be 1 line of code, and I'd be on the business value, getting what we need from it, not busy trying to go,
just scrap the structure together to get something to run and dealing with the compiler. And yeah.
Well, so you started talking there about getting things working, and I saw you mentioned the other day 3 rules that you abide by when approaching application development. Could we talk about that and how you use it when you're approaching HPC or any development that you're doing?
Yeah. No, that's a good question. So I'd say rule number 1 is that it's more important to be correct than fast. And maybe I'll go through all 3 and then, we can touch on each one. So more important to be correct than fast. If performance is a requirement for your application, then you need to make it a requirement. It needs to be written down, and you need to have, reasons why this number is needed. And then when you're initially kind of developing a feature, and let's say performance is a requirement, it's better to write, reasonably performant code in 2 days than it is to write that same highly optimized code in 2 weeks. And so maybe we start at number one, probably the most important. That's why I like it as number one. It's more important to be correct than fast. And well, the reason for that is that we it's almost self-explanatory. We need correct results. Correct is kind of arbitrary. Correct doesn't always mean the same thing. Sometimes it's okay to be kind of correct, or sometimes it's okay to be, like on a distribution of correctness. So let's say, you have a big curve and we're okay being somewhere here. That's fine. But just defining what that criteria is for correctness, and then ensuring that you're meeting that criteria with your software. And another one in this space is like correct in terms of, especially in C++, like we're not writing over illegal memory. We're not accessing illegal memory. We're not doing things. That's one thing that is maybe more challenging about GPU development is a lot of times we're just feeding in this very large array, and we have a lot of different threads writing into different indexes in that array. And if you're not correct in your mental model about how you're dealing with data is wrong, some of your threads are overwriting the data from other threads, and everything is just wrong, right? And a lot of times that can be in a just obscure, maybe a small part of your array. But yeah, you need to start there before you can kind of go anywhere else, correctness.
Yeah, I imagine if that was one layer of your neural network, it'd be incredibly hard to spot that you're just blatting over a couple of the neurons and the calculations from there.
Yeah. And timing, like we talked about networking and distributed, calculations, timing can even begin to play a very real role here. And you can have subtly incorrect code that looks correct 99.9% of the time, and you introduce it to a new data set or something, and that exposes some logic flaw somewhere even in your parallel application. You have something that's just a little bit wrong and you never see it, and then all of a sudden you do see it. You're like, I'm getting non-determinism here, right? That's like I don't get the same answer every time, and it shows up 3 months after you developed your original code, and it's because you gave it new data or bigger data or something, and it's exposing a mistake you've made early in your process or your pipeline. It's hard to deal with. Yeah. So, and then number two is, if performance is a requirement, make it a requirement. And this comes from like a lot of sort of hand waviness of like, I want this to be faster. And then another thing I see newer developers focus on a lot, and it's not necessarily a bad thing, but like they come out of, let's say, data structures and algorithms, and they're like, I can make this function faster, right? You can spend kind of unlimited time optimizing code, and you can hyper focus on, eliminating an instruction in a function or whatever and making it a little bit faster. But what you see with this stuff is people don't often know going into things how fast or what type of number they need to meet to make, really, at the end of the day, it's like make your customer happy, right? And they don't actually know what that number is. And it usually comes over time where like customers aren't really satisfied if my latency is this number. So let's push that latency number down a little bit. And how can we do that? And so we set our first threshold. One in LLMs, right, is it's called time to first token, and then inter-token latency. Those are big ones. And what they found is that you really want to be able to keep up with the speed that a human being can read, right? So like you want to
That
go a
makes
little
sense.
faster, yeah, than a human can read as you're spitting, letters to the screen, so they don't have to just wait a whole long time to do that. Yeah, and it by making it a requirement and picking a number, whether it's arbitrary or real, or just sort of based on intuition, like you give a first thing to shoot for, it allows you to better structure the rest of your timelines, your requirements, and keep people in scope and focused. Yeah.
Cool, yeah. And that brings us then to 3. Focus on what's reasonable performance in 2 days rather than higher performance in 2 weeks.
Yeah. A lot of juice around this one too. So like we want to get to the reason we do that is maybe a few fold. We want to generally, when we're developing, an application, we're broken up by features or some subset of features or sub feature even. And if we can get something done in 2 days, then we can keep the rest of the application kind of moving forward, or we can build on to the next step, right? We can get to our final thing and make sure our final thing is correct. And it's like the thing that people want. And we can QA and user test and all that stuff to make sure it's doing what we want. And that like kind of keeps the whole project moving forward. Eventually somebody else is going to be blocked by your missing feature, or, if you're working in a team, the whole thing is going to be blocked because you haven't gotten your piece in yet. And if the reason you haven't completed it is because, well, I'm just trying to make it a little faster or a little better, like that's just kind of annoying for everybody. And maybe a more practical reason is I've been guilty of this. I've seen everybody I work with be guilty of this. Somebody goes through it at some point. You often are optimizing the wrong thing. So there are many components in these larger applications, right? And we are just picking one small thing, and by the time we're done, we realize where our bottlenecks are. So if we go through and we profile and we look at the whole thing as a complete application, we really usually have maybe 2 or 3 parts of our code. We'll call them critical paths that take the most time. They maybe each share, maybe one is 40% of the runtime, one is 20%, and another is 20% or 10% or whatever. And then the rest are like 1%, right? And in doing what you're doing with a feature, you might be developing one of the 1% or the 0.5% of the total runtime features. So spending all your time or any additional time, wasted time optimizing that is immediately diminishing returns. It provides almost no value, and it's negative value because you're taking time away from more important things. Yeah.
Yeah, absolutely. And I saw a great example of this, Dennis, when I joined that project that was doing the HPC stuff, in that one part of the system was taking 7 minutes. And it was going lots of times, 7 minutes each time. And the guy had spent a week optimizing this. And he was trying this, trying that, reducing 2 or 3 seconds here, 10 seconds there. And I came along and said, well, cool, but this seems a bit kind of scattergun. Have you profiled it? And he just looked at me a bit bemused. So we ran it through a profiler, and the profile showed exactly where 6 minutes were being spent.
Yeah.
And I looked at this and went, well, I'm fairly certain NumPy will have a function that does this.
Yeah.
So we pulled out these 5 lines of code that were taking all the time, and we replaced it with one call to NumPy, where sure enough it had a function that did it. It went from 7 minutes to 7 seconds.
Yeah. Yeah.
Again, not because we did anything amazing. It was like, where's the bottleneck? Oh, cool. Right, we're doing stuff here that Python sucks at.
Yeah,
NumPy is designed for.
yeah,
Let's call the function that's highly optimized by people much cleverer than us in NumPy. And it made a huge difference.
that's exactly it. Yeah,
So the other thing I was thinking about there is I agree with everything you said. One of the other points I've brought, less from the point of view of HPC, so that's why I want to ask you about it. So I've made the point many times with engineers that work for me that sometimes with performance, their time is much more valuable and our time to market is much more valuable than hardware.
yeah,
So if the performance is good enough after 2 days and we want it faster, we can go and buy a bigger compute, or we can go and rent one by the hour from cloud provider of choice. And that's almost infinitely cheaper than developer time. HPCs and GPUs tend to be a bit more expensive, and there's been a few shortages. But how does that compare with when you're doing HPC stuff with, get a bigger computer versus spend time optimizing it?
yeah. It's kind of the same rule applies there. Developer time is more expensive than compute time. We want to just make sure, and that's the other, the goes back to rule number two is um, companies, they have these SLAs and they have these guarantees they provide their users. And if an application or a setup like meets the SLA or is close to it, and you can kind of figure out a way, maybe buy a bigger computer, because there are different, there are different tiers. We might try to run something on a smaller tier GPU because it's less expensive, but you will just get that for free, that performance boost you need if you went from say an A100 to an H100, which are um, different NVIDIA GPU models. And if that's the case, then like we don't need to try to optimize this thing further today, uh, unless someone tells us. But they may be perfectly okay with, yeah, this works on an H100. We don't even have to tell them, It's like we know that this works on it, whatever. And we can go and then build the next thing, and continue to make the whole offering better rather than hyper focusing on kind of this one area. So, it can be give and take there. I think it's maybe a little grayer when it comes to HPC, and that sometimes you really do need to drill into making the thing. Like at my old job, we knew what our setup was. We knew what our performance requirements were for, we'll say, almost real time processing of data. And in that instance, we came up a little short, like our first pass through our end to end, like kind of feature delivery for our first customer. And we knew that we needed to trim a couple seconds off of the whole application. And we knew that the hardware we had was the hardware we had because it was a device. So we were shipping a device, and we could not change the compute hardware there. So we just needed to make it faster. But if that's not the case and you have access to other machines and you can use better GPUs, say in a cloud environment, or you have access to resources to buy newer compute, yeah, don't focus a whole bunch on that last 2% unless you really need it. Yeah.
Yeah, that reminds me. It's quite interesting. So I never thought about performance from that point of view when we were doing HPC, because we had this big cluster and we could scale to a bigger, use a few more nodes, as well as optimizing our code. So we generally erred on the max of use more nodes. We bought the computers, let's use them. The interesting part from that, and I didn't touch this, is that some of the stuff that was written in C was going on an embedded device.
Yeah.
So you're right there, that was at the opposite end of the spectrum. This is a tiny embedded chip that sits inside another system.
Right.
That is woefully underpowered compared to most desktops these days, because it's a small embedded chip embedded in a computer. So they had the complete opposite end of the spectrum. They really had hard constraints on the hardware, and they had to optimize everything to get this machine learning algorithm to work in that device. So
Yeah.
Complete opposite end of the spectrum. A tiny embedded system to HPC.
Right.
But cool.
Yeah.
It makes life interesting. So thank you very much for your time, Dennis. It's been great talking about HPC. If somebody wants to learn more about HPC and what you do, what are good places they could reach out to you if you're open to that? Or what are good resources they could turn to?
No, yeah. Thanks for the time. Also, I always love talking about this stuff. Yeah, I think I'm on LinkedIn. Shoot me a DM on LinkedIn. I have a little GitHub with CUDA examples. I think if people are trying to kind of dabble into CUDA, compiling and running that code and that repo is a good kind of jumping off point. NVIDIA has CUDA samples, but I feel like it's a little bit all over the place and maybe hard to approach. So I took a little different approach to dip your toe in. And then if people want to like learn how to play with, I can speak to. It's actually really hard to find, good quality HPC material, and so I feel like GPUs are a good proxy to that. Like you don't just get access to a data center. It's not a. People ask me, and I'm like, yeah, you got to like get a job, and so there is a accelerated computing repository from NVIDIA, and they have like notebooks, like Jupyter notebooks, where you can go and go through their GitHub and kind of this course structure to get up and try to learn a little bit about CUDA that way, and then books, data, Kaggle, just kind of play around. Yeah.
Well, so there's an idea for Raspberry Pi Foundation then. Build a small HPC cluster of Raspberry Pis, a few NVIDIA GPUs.
That's right. That's right.
HPC in a box.
I've thought about it. Like, let's get a course set up. I'll build a data center in the backyard with a couple nodes, and people can connect from all over the world. Yeah.
Awesome. Cool. Thank you very much for that time, Dennis. It's been an absolute pleasure talking to you.
You too, John. Thanks for your time, and love being on the pod today.